Let's look at how we can solve linear systems of ordinary differential equations using linear algebra. So recall the typical first order differential equation, which is the first order derivative being equal to a constant multiplied by the dependent variable. And this is well known to have a general solution, which is a constant by the exponential function raised to the power of k by the dependent variable. So y can be a function of x, time, and so on. So from this general solution, a particular solution can be obtained by using an initial condition. So this is an example of y at x equals 0 being equal to 2. So if you apply this to the general solution, we have 2 is equal to the constant multiplied by e to the power of k multiplied by 0. So e to the 0 is 1, and therefore our constant is 2. And therefore the particular solution is 2e to the kx. So we can extend this method of solution to first order linear systems of ordinary differential equations. So in this case we'll have multiple differential equations which depend on multiple independent variables. So we'll have a constant by y1 plus another constant by y2 and so on, plus another constant by yr. And similarly, we'll have an equation for the first order derivative y-2. So that will be the constant a21 by y1 plus a22 by y2 and so on, plus a2r by yr. And this continues up to the rth differential equation. So we have a constant ar1 by y1 plus another constant ar2 by y2 and so on up to arr by yr. So when solving this system, the functions to be determined are y1 being some function of x, y2 being another function of x, and so on up to yr being another function of x. So in general, we can write this system in matrix form. So we have y dash is equal to the matrix of coefficients multiplied by y. And this is the general matrix form of the first order linear system that we'll be solving. Consider this first order linear system. Well, because the matrix of coefficients is diagonal in this case, we have three independent equations. y-1 is 2y1, y-2 is minus y2, and a derivative y-3 is 4y3. And now you can apply these initial conditions to solve each differential equation individually. So in the first case, we'd have y1 is equal to a constant of integration by e to the 2x, and y2 is another constant of integration by e to the minus x, and y3 is another constant by e to the 4x. So therefore, applying this first initial condition, we'd obtain minus 3 is c1 by e to the power of 0. So c1 is minus 3. So what we'd get is y1 is minus 3 e to the 2x. And similarly, applying the second initial condition, we'd have 2 is equal to c2 by e to the 0. So therefore c2 is equal to 2, and we'd get y2 is 2e to the minus x. And similarly, y3 is 4 e to the 4x. So if you differentiate these equations and substitute them into the original differential equations, then you'd see that the left-hand side satisfies the right-hand side. So therefore, to solve a general first-order linear system, being y dash is equal to the matrix A by y, where A is generally not diagonal, we can diagonalize this system. So if we let y equal to a matrix P by a vector V, then y dash is P by V dash, and that's equal to A by y, which is P by V. And if we multiply by the inverse of P on both sides, we'd get V dash is equal to P inverse by A by P, and that's multiplied by V. So assuming the matrix P diagonalizes A, then V dash is equal to a diagonal matrix, being this matrix, multiplied by V. And therefore we can now solve this system for V in the same way that we solved this system, because we have a diagonal matrix, and therefore once we obtain V, we can multiply V by our matrix P to obtain Y, being the general solution to our first order linear system. And then a particular solution is obtained by applying the initial conditions. And we'll do this in an example. Let's find a particular solution to this first order linear system. So we can first write this in matrix form, where we have y dash is equal to the matrix of coefficients multiplied by the solution vector. And we'll let y equal to the matrix P multiplied by V, and P is the matrix that diagonalizes A, being the coefficient matrix. And from this, we rewrite this system as V dash being equal to P inverse by A by P by V. So to determine P, which diagonalizes A, we find the eigenvalues and eigenvectors of A. So we take the determinant of A minus lambda I, which we've done before, and set that equal to 0. So this determinant gives the characteristic polynomial. So we'll just multiply the terms on this diagonal and subtract 4 by 2. So that gives lambda squared minus 3 lambda minus 1 lambda plus 3 minus 8, which is minus 5. And then factorizing this, we get lambda minus 5 and lambda plus 1. So our eigenvalues are lambda 1 is equal to 5 and lambda 2 is minus 1. And then to obtain the eigenvectors, for lambda 1, we have 3 minus 5 and 1 minus 5. And we'll augment that with 0. And therefore adding row 1 to row 2, we get zeros. So therefore we can write the solution of eigenvectors as v1 is equal to 4 on 2 v2. And if we parameterize v2, so set that equal to t, then what we'd get is our general solution being equal to t by the basis eigenvector. And in a similar way, for lambda 2 is equal to minus 1, we have 3 minus minus 1, which is 4, and 1 minus minus 1 is 2. And we'll augment that with 0. So therefore subtracting 1/2 by row 1 from row 2, we get zeros. So therefore we have v1 is minus 4 on 4 v2, or v1 is equal to minus v2. And again parameterizing v2, we can write the general solution as t by the basis eigenvector for the eigenspace of lambda 2. Now let's make a bit of room over here. So therefore our P matrix consists of the basis eigenvectors in each column. And if you take the inverse of P, multiply it by A, and then by P, then you get a matrix with the eigenvalues on a diagonal. So we have 5 and minus 1, which correspond to each eigenvector in those columns. So our system becomes V dash is equal to this diagonal matrix by V. So we can rewrite this system as V1 dash is equal to 5V1 and V2 dash is minus V2. So the general solution to each of these equations is V1 is equal to C1 e to the 5x, and V2 is another constant of integration by e to the minus x. And now using this equation, we can obtain a solution vector y. So let's do that here. So we have y is equal to our matrix P multiplied by the solution vector V. So that would be C1 e to the 5x and C2 e to the minus x. And now let's make some room over here. So multiplying this out, we have y1 is 2c1 by e to the 5x minus c2 by e to the minus x, and y2 is c1 e to the 5x plus c2 e to the minus x. And now we can apply our initial conditions. So y1 of 0 is minus 3. So from the first equation we have minus 3 is equal to 2c1 by e to the 0 minus c2 by e to the 0. And our second initial condition gives 2 is equal to C1 plus C2. And now we can solve this system for the constants C1 and C2. So let's construct our augmented matrix where we have 2, -1, 1, and 1, augmented with -3 and 2. So if we use Gaussian elimination, we have row 2 minus a half by row 1, which gives 0, and 1 plus a half is 3 on 2, and 2 plus 3 on 2, which is 4 on 2 plus 3 on 2, or 7 on 2. So that gives 3 on 2 by C2 is equal to 7 on 2. So C2 is 7 on 3. And we can substitute that into here. And from the first equation, we have 2C1 minus C2, which is 7 on 3, is equal to -3. So if we multiply through by 3, we get 9 and 6. So 6C1 is -2, which implies C1 is -1/3. So what we'd get is -2 on 3 here, and -1/3. So this is the particular solution to our linear system. So you can differentiate both equations and check that the left-hand side is equal to the right-hand side, which I'll leave for you as an exercise.